and Mr. Eric Stoneking, and I want to introduce him properly. If I can just be given 2 seconds. Actually, what I wanted to do was to put your bio online, but I mean on the screen, but I'm gonna read it, okay? So, so it is my pleasure to introduce to you Mr. Eric Stoneking, who is a senior engineer for the senior engineer for the ACS Systems Branch at NASA Goddard Space Flight Center. He's currently the ACS Analysis Lead Engineer for the Nancy Grace Roman Space Telescope project. He has 30 years of experience in spacecraft dynamics and controls, 20 of those at Goddard Space Flight Center. He received a Bachelor's of Science in Aerospace Engineering from Tri-State University and an MS in Aeronautics and Astronautics from Stanford University. And his catchphrase is F equal to MA, all the rest is accounting, which I find so catchy. Eric, should I say tri-state or tri-state? I'm sorry.
Tri-state.
Tri-state, okay, good.
Yeah.
All right, great. So please, let's all welcome Mr. Stoneking, who actually will be so generous as to give 2 presentations to us. The first one is about the implementation of Kane's method for a spacecraft composed of multiple rigid bodies. Please, Eric, go ahead.
Thank you. Thank you, Fabrizio, for inviting me to speak here today. And it's very nice to see the kind of the lead-in was a talk about Feynman and you know, doing mechanics from the very basics. So what I'm going to talk about here for about half an hour, and then I'll talk about 42 more in particular. This is the core of the multi-body dynamics formulation that is in 42. Kane's method is an approach to deriving equations of motion. So this is a talk that was put together about 10 years ago, and I put it together, but I never had the chance to actually present it myself. So this is the first time, and now I have to figure out how to move my screen. All right, let's try this. So here's the outline. I'm going to talk about some features of this formulation and introduce Kane's equations of motion and talk about rearranging those. And then some of the building blocks that make this all possible, partial velocity matrices, joint partials, and expressions for accelerations. And then I'm going to put it all together, and then at the end, I'll just talk a little bit about an example problem that kind of proves the implementation concept. So what I'm going to talk about is a multi-body dynamic formulation. It handles general tree topology configurations without regenerating code. So a tree topology is just a collection of bodies that are connected together in a way that there aren't any loops in the structure. Regenerating code, if you, right, I want something general. So if I have one spacecraft, I can derive the equations of motion. If I have another spacecraft, I don't have to go back all the way to the beginning. I want to be able to represent the spacecraft through input files. I can say what the masses are, where the joints are, things like that. I want this all to be done through input files, and then the computer takes over from there and does the dynamics. What I'm going to concentrate on today are rotary joints, spherical joints, 1 or 2 axis gimbal joints. I'll mention translational joints from time to time. When I wrote this, I had only implemented the rotational joints. After that, I have done translational joints. So 42 supports all of those, all of that now. The great thing about Kane's method I gotta say, is that when you assemble a bunch of rigid bodies together and connect them and so forth, the motion is constrained by all those connections. And managing or handling, how do you find out what the dynamical equations are without having to also solve for all the constraints? There are various ways to do this. Well, there are various ways to do it where you're solving for the constraints at the same time as you solve for the dynamics. It's more work, it's more computational. You get into numerical issues. So the great thing about Kane's method is that it separates the dynamics from the constraints. So you never have to solve for the constraints. I mean, you can if you want to, but generally I don't want to. I just want the dynamics. This yields a minimum dimension set of equations. So there's only as many equations as you need to solve. And that's good for saving just computation effort. And like I say, I'm going to concentrate on rotational joints today, but and rigid bodies, but you can extend this to handle multiple flexible bodies and also translational joints. And I have, since this presentation was put together, I have implemented those in 42. So Kane's equation, can you see my cursor here above the first equation?
Yes, yes, I can see it.
Awesome. So the way Kane's equation is presented is just this very elegant looking thing, FR plus FR star equals 0. Of course, the more concise the notation gets, the more words you have to use to explain it. So let's unpack this a bit. What the subscript R here is I've got so many degrees of freedom. So for the rth degree of freedom, I'm going to have an equation. And the pieces that go into it, the first term is what we call generalized active forces, okay, which if we look at this, I'm going to have a bunch of bodies, okay, a bunch of rigid bodies. So I'm going to sum over those bodies. So I've got a kth body. I'm going to apply some forces to it. That's what this F is. This is the F sub K is the forces exerted on body K. And I'm going to have some torques. I exert some torques on that body. And I'm going to multiply by some factors here. And I'm just going to say, I'm going to name them, and then we'll talk about them a bit more in a bit. These are the partial velocities, and these are the partial angular velocities. And if you perform these dot products, then you get the generalized active forces. Generalized active force just means forces and torques, okay? So that's what FR is. And when you add the star on it, that means we're talking about inertia forces. Well, what's that? So if you look at MA, as in F equals MA, this MA with a minus sign, you can think of that as being a force exerted by the inertia. Similarly, for rotational motion, you end up with an expression like this, which has the moments of inertia, the angular acceleration, and an extra term that comes about the angular velocity crossed with the total momentum of the body. Okay, so that's what FR star is. And you know, are we any better off for knowing that? What we're going to do next, I think, does shed some light. When we add these terms to redistribute these terms like this, this actually starts to look familiar. There's F equals MA right in there. This one here is called Euler's equation. It's the equivalent of F equals MA for rotation of a rigid body. The torque equals, or sorry, it's usually written as, doesn't matter. The inertia times the angular acceleration is equal to the torque minus this omega cross h term. So now I see things that are familiar now. And I think, whenever you're doing dynamics, you should go looking for these. Where is F equals ma? It's in there somewhere. Well, what I've done here is I've multiplied them by these factors, the partial velocities and the partial angular velocities. And what's very special about these is these are the factors that that separate out the dynamics from the constraints I was talking about. One way to say it is that they project these equations of motion into the subspace, into the motion subspace, the space that the things can actually move in. So that's a profound thing. It's a marvelous thing, and it's actually easier than it might sound to work with these things. I'm going to talk about that on the next slide. But here we go. We've got this equation now. And we're going to present this in a different form as we go along. And to solve this, but when I say solve, I really mean I want to write the equations of motion in a form that I can solve them on a computer with a numerical integrator. So to set them up, to write those equations, I need to develop some of the pieces. We can say that at any particular point in time, we know what the torques and the forces are exerted on our spacecraft. We know what the mass is. We know what the moment of inertia is. At any particular instant, we know what the angular velocity is and the total system momentum. What we don't know are the angular accelerations and the linear accelerations. Those are the things we have to solve for. So, and at a particular point in time, these partial velocities and partial angular velocities are also functions of the configuration. So what we're looking for is those building blocks. We need general expressions to express those partial angular velocities, angular acceleration, and linear acceleration. So that's what we're going to spend a few slides doing. So let's talk about the partial velocities. The first thing we do is we talk about generalized speeds. These are our dynamic states. For one body, I'm just going to say I've got an angular velocity vector and a linear velocity vector, the velocity of the mass center of the body, and the angular velocity of the body. And I'm going to put those together, and I'm going to call that vector u. So there are going to be 6 elements in u, and u are going to be my generalized speeds. As I start adding bodies, I add degrees of freedom, and for each degree of freedom, I want to add another generalized speed. So for 2 bodies, I'm still going to use the omega of the first body and the velocity of the first body as my state variables. I'm going to introduce another variable. I'm going to call it sigma. It's just the speed of that's in the joint. So if I've got 2 bodies, they're connected by a joint. If I've got n bodies, then any particular body, I can figure out what its velocity is and what its angular velocity is by knowing what the first body is doing, and then what all the joints in between the first body and whatever body I want are doing. So this is the minimum number of variables that I need to describe the motion of the system. All right, I'm going to call it this vector u, generalized speeds. And then I'm going to say what I sort of said in words already, that for any body in my system, I can describe its angular velocity vector and its linear velocity vector as some function of these generalized speeds. Okay, and the nice part about this is that it's a pretty straightforward to do. If you look at a system, the first thing you do is you say, well, how can it move? And if you can describe how it moves in terms of its generalized speeds, then you just build these matrices. Okay, I've got them in matrix form here, but these are those partial angular velocities, and those partial velocities all just assembled into matrices now. And yeah, you build those up pretty much just by inspection, by looking at your system. Okay, so we want to mechanize that process so that we can put our descriptions into input files and have the computer build these matrices during the course of the simulation. Okay, I'm going to talk about joint partials. Is this sigma here is the generalized speeds related to a joint, and I want to relate that to the relative angular velocity of an outer body with respect to an inner body. So for any joint, I'm going to say that there's a joint connects two bodies, an outer body and an inner body. And if the outer body can move with respect to the inner body, it's going to have a relative angular velocity, and it's related to whatever the joint speeds are by some matrix here. And the details of this matrix depend on the details of the joint. If it's a 3 degree of freedom joint, then you're going to have 3 columns in this matrix. If it's a 1 degree of freedom joint, you're only going to have 1 column in this matrix. But there are only so many different gimbal joints, so I can say, let's just call them all gamma, so I can put them under one umbrella. And then if you tell me more about the joint, like it's a 2-1-3 Euler sequence, then I can tell you exactly what goes inside here. And just a notational thing, these C's and S's are short for cosines and sines of like the second and third angle in the sequence. So if at any particular time I know what the angles are, then I can tell you exactly what this matrix looks like. So having no better thing to call this, I call this the joint partials. It's just what is the relative angular velocity as a function of the joint speeds. All right, and a special case, a spherical joint, like a ball and socket joint, the degrees of freedom here are just the same as the angular velocity components, and this gamma matrix becomes an identity matrix. So the important thing here is that for all these different kinds of joints, I can bring them under one umbrella symbol and just call it gamma. And when it comes down to actually doing it, I can refer back to what that actually means. But for the formalism, it's nice to have a single letter, and this is why. So I'm going to look again at this system where I've got one joint connecting 2 bodies. This is the inner body. This is the outer body. The joint is at some vector from the mass center of each body, and I call that Ri and Ro. The joint itself, I call it, this is the kth joint, so G is for joint. And I can say that the outer body's angular velocity and linear velocity are related to the inner body's angular velocity and linear velocity, plus some other terms. The angular velocity has that gamma sigma that we saw on the previous slide, and the outer body has some omega cross R kind of terms. So if I differentiate those, I get my angular acceleration of the outer body, okay, related to the angular acceleration of the inner body, plus some other stuff. All right, and this is something I need. I need all the angular accelerations for all the bodies, and the linear accelerations. But I'm not quite to where I want to be yet. I'm going to take another step, and that is, as I develop these, I notice that this dot here is differentiation with respect to time. So there are terms that appear with the derivatives of my generalized speeds. Okay, and then there are a bunch of terms that that don't involve the generalized speeds. So I'm going to group those together. So what turns out is that the angular acceleration, if I look at like the whole system, I've got my partial angular velocity matrix times u dot plus some leftover terms. I call those remainder accelerations. And they're just all the terms that are in these acceleration expressions that don't involve u dot. And the nice thing about those is that I can build those recursively. Okay, if I know the remainder accelerations of my inner body, then I can find the remainder accelerations of my outer body for each joint, right, by adding these terms. So great, I've got these expressions now, and now I can build in an efficient manner all the angular accelerations for all my bodies in my entire spacecraft. And now we can put it together. So this equation here is hopefully a recognizable transformation of what I presented in the opening slides. Okay, right here, there's F equals ma. Here is the Euler's equation part. And this omega and v are the partial velocities and partial angular velocities in matrix form. And I've spent the last couple of slides finding that I can represent angular acceleration as this expression and linear acceleration as this expression. And now I can group on these u dots. And so what I end up with is this equation here, which is in the form of there's some matrix times these u dots equals some vector. And the dimensions of this are exactly as many dimensions as I need to represent the motion of the system. So this is a minimal size set. And they are linear in the variables that I need, my u dots. So I can put this into a numerical integrator, solve at each time step, solve this linear system of equations, find my u dots, and propagate those. Okay, so just to prove the implementation works, I ran through an example problem. So this is a story from the beginning of spaceflight. It's a minor axis spinner. Explorer 1 was a satellite that was put up. It was basically a top of a missile. But it had some wire antennas, which I have modeled here in some fashion, right? It's just these pinkish bars. And I've put some flexibility in at the joints between the main body and these small bodies with some damping. So there's a little bit of energy dissipation. So in your first dynamics class, you'll learn that a rigid body, if you spin it about its major axis of inertia, that motion is stable. If you spin it about its minor axis of inertia, that motion is stable. And if you spin it about its intermediate axis, that motion is unstable. But if you take a second look at it, the energy dissipation causes the minor axis motion to, over time, destabilize, and it'll end up as a major axis spin. Angular momentum is conserved the entire time, and energy seeks a minimum. Okay, so I performed this experiment through simulation. I started out with a minor axis spin. The numbers might be a little tough to see here, but this is 3 hours in. It finally diverges. And then 5-6 hours in, it's settled into a major axis spin now. And just to check, the kinetic energy went from 2.5 something to about 0.4 something. So we had a reduction in kinetic energy. And I don't show it here, but momentum is conserved. And just as a check, if I take the same system and lock all the joints, so there's actually no freedom in there, then it stays at a minor axis spin the whole time. So what I've tried to demonstrate is that I do have multi-body dynamics. The bodies are interacting with each other, and it reproduces a result that we knew. All right, so Kane's method is great for separating the dynamics from the constraints in a dynamical system. It uses the partial velocity concept to take Newton's equations and Euler's equations for rotation, and it projects them into the subspace of permissible motions. And so by construction, it eliminates all the constraints, which is great. I talked about some dynamic building blocks and how we can construct them recursively, the partial velocities themselves and the remainder accelerations. The resulting equations are suitable for computer solution. As I don't know, maybe you could have gotten this from the Feynman lecture earlier, but what we're trying to do here is get the answer, right? So we can talk about philosophy, but really I want to set up the equations so I can solve the equations and actually see what my system is doing. And then some of this future work is now past work. I have implemented multiple flexible bodies and translational joints. Kinematic loops, I think I've got an approach for that, but I haven't actually done it. I need some quiet time to sit down and do that. But that's where the state of things is now. Okay, so that's the conclusion of that. I'm happy to take questions.
Well, first of all, please let's all thank somehow. Let's make some noise to thank the speaker here. Thank you so much for this wonderful lecture. And honestly, I, as a teacher, I wonder. I mean, obviously, when we think about constraints, we think about Lagrange. And I'm wondering if, for the sake of those who have gone through that kind of an approach, could you contrast under any respect, whether it be computational or any other, the traditional way of dealing with constraints with the Kane's approach? I mean, I understand that you can eliminate the constraints, but for instance, computationally, is it that expensive to do it traditionally?
So, the short answer is yes, and the longer answer is since you're setting up a system of equations that's basically a linear system here. Okay, the way that you typically solve that numerically is with Gaussian elimination and backward substitution. And the computational complexity of that goes like the cube of the size of your system. So you double the size of your system, your computational load goes up by a factor of 8. So you're motivated to minimize the size of your system. The example that I talk about is, say you've got just two bodies, right? So I've got one potato and two potatoes, and I connect them with a hinge. I had 6 degrees of freedom in this potato, 6 more here. That's a total of 12. I connect them with a hinge. That takes away 5 degrees of freedom, so I'm left with 7. Okay, so the minimum number of equations I need is 7. One way of doing the system, though, is saying I'm going to have 6 equations for this one, 6 equations for this one, and then I add 5 constraint equations. And those were those differential algebraic equations, DAEs. But if you say 6 plus 6 plus 5 is 17. So if you look at the difference between 7 cubed and 17 cubed, okay, you can see you're doing a lot more work. And even, you know, even with computers, this can get out of hand pretty quickly. Now, Lagrange's method is a different approach to deriving the equations of motion. But you should, you know, knock on wood, you get to the minimum number of degrees of freedom that way. I find that for rigid bodies, I like this approach better. There's some things about Lagrange that I find a little bit awkward, like you're taking a derivative of a q dot. You notice through this whole talk, I've talked about generalized speeds. I haven't even mentioned generalized coordinates. Right, I use them a couple of times. The thetas in the joints and so forth. Those are generalized coordinates, and Lagrange starts with those and then takes, you know, q dots and then another derivative with respect to time. But one of my favorite generalized speeds, angular velocity, it isn't really there's no q that where q dot equals omega. Right. There's you can do q's where q dot is some function of q and omega. Okay, so you end up, you know, putting that in there. But you can I just find it a little more straightforward to let's just talk about omega, and it falls out very naturally from this kind of way of looking at things. I start right with you know, the closest thing you can get to F equals ma for a rotating rigid body, Euler's equation, and my dynamical state omega is right there. I'll say Lagrange's method, I think, is great for particles. Particles in potential fields, it's very natural there. I think that's where a lot of people use it.
And just for as a matter of background for those students who may not know, Explorer 1 actually was a famous case because I don't think that they were expecting the behavior, right, when they launched it.
No, they weren't. They thought minor axis spinner were good. And then hours later, it comes up into view and it's tumbling in a flat spin. And they go, well, how'd that happen? And then they went back and, oh, yeah, okay. The answer is, it was like they knew the answer in the back of their head all along, but they didn't think about it until they actually, you know, and they saw it, and then they had to go explain.
So the flexible joints were the source of this behavior, basically, at that time.
Yeah, I just modeled it as I put all the flexibility in the joint itself. On the real spacecraft, they were whip antennas, so the whole antenna is kind of floppy. But it doesn't matter. The important thing is any energy dissipation you've got. If you had fuel on board that could slosh, just anything, wherever there's energy dissipation, it's going to cause. Where'd I put it? Any energy dissipation is going to drive you toward that major axis spin.
Great. All right. Great. And is this also a hidden feature of 42, or is there documentation for the?
I don't know if I still have this example hanging around anywhere. It's not in the public distribution, but you can certainly set up a system like this easily. Yeah.
It would be great. Because I would love to include this maybe in spacecraft design or something class, and but it's always good to have a recipe to start that you can check whether your numbers are coming out right. So if you have anything that you can leave us so that we can follow the master, that would be great, you know, if it is allowed.
Sure. I can maybe when we talk later about 42, you know, I walk through some things. Maybe as part of that, I can just point out, you know, this is where you would set up a system like that.
Sure. Thank you so much. And,
yeah, this is a pretty simple thing to do.
Well, I doubt that, but it's but it is an interesting thing to do. So I also have one follow-up question that I will ask more or less every FOSS speaker today. And please tell me when you would like to deal with this. But what got you to the point of deciding that 42 would be a free open source product instead of, I don't know, for instance, trying to sell it, trying to, you know, become a company or something like that? I mean, why are you doing this? Would be the fundamental question. I don't know if you would like to discuss that now or later.
Yeah, I can do that. Well, let's tackle that now.
Thank you.
Yeah, so for one thing, right, I lived through the early days like you did, and it's very annoying when you build up a tool set and then, you know, based on some commercial product, and then that commercial product gets bought by somebody else and shut down. I know you had to have seen that happen. I've seen that happen.
Right. I know. Yeah.
All right. So so that's one factor. I've been on the receiving end of commercial stuff, and it's annoying. On the other end, I have kind of some you know, so I've got personal motivations for having this be publicly available that are actually, you know, less altruistic than you might think. If I have a product and I want to make it available to another project inside inside NASA, inside Goddard, there's paperwork that has to be filled out, and that paperwork takes time and is kind of annoying. Are we still recording?
I can stop you.
No, it's okay. It's okay. It's
okay.
right.
Okay.
That's just a joke.
Okay.
Okay then.
But if something is open source and some project says, "Hey, Eric, you got that thing? Can I have a copy?" I can say, "Yes, you can download it from GitHub." Okay. So I had to go through the process of getting it to where it could be open source, but having done that, it makes it a lot more available to customers within Goddard, within NASA. You know, and just having it available to every college student in the world is a side benefit.
Well, and I would not want to diminish, for the understanding of those who are listening to this, I would not want to diminish the fact that it doesn't have to be altruistic in the naive sense of the word. I mean, if there is an advantage to be derived from open source work, that actually strengthens the hand of this concept. It doesn't weaken it in my mind. I mean, so that would be better if you could show that there is a strategic advantage in pursuing something like this.
Yeah, I agree. I did spend some effort to make it cross-platform and hopefully, you know, easy to get into, right? Easy to get a case up and running and get at least some kind of a result out. And part of that is just because I wanted people to be able to use it so that people would use it so that I could continue to use it.
Which is also another issue that perhaps young people cannot understand. But if you pursue a product from within an organization, and this product is on GitHub, in the second part of your life, if you want to become a professor or something like that, you can take it with you, but otherwise you will leave it behind, right?
Yes. I spent 10 years in the private sector before I joined NASA. And I started writing 42 when I joined NASA. I left all my old tools behind and started from scratch. Because the old tools, you know, I didn't want any problems about my old, you know, private sector company asking me about, you know, hey, are you using tools that we paid you to develop? Well,
Yeah,
the answer is no. I started fresh, started from scratch, and you know, built 42 up that way.
And this is C++. Is it that you use for this?
Most of it is ANSI C. It is straight vanilla. I wanted it to be as you know, as unfancy as possible, just so that it would be as portable as possible. Okay,
got it. All right. Well, then this is absolutely fascinating. Obviously, the students will need to digest some of the issues that you have raised, and I am on the receiving end of that now. So we will discuss it. But I mean, what I was thinking is that, as you know very well, this is another conversation following Feynman, is that at some point modern physics became fashionable, and it looks like the only important questions that are left to answer are hidden, you know, in elementary particles or something like that. Whereas there are these issues with rigid bodies or flexible bodies in classical mechanics that are very hard to solve, and they remain very hard to solve today.
Yeah.
So are sails, to give you an example. You know,
solar sails is an awesome problem. I can't say too much about that. It's you are coupling attitude dynamics and orbit dynamics. Your environment is your control system. Yeah, it's great stuff.
Well, thank you so much, Eric. So let's do this. Unless there are any questions from the audience, I see that David has arrived, and he was made co-host. So I don't know if you would like to join in the conversation. Sometimes I break these questions into a little bit of a round table. So while you guys think whether you would like to have questions, so there are a couple of people that I would like to introduce so that the conversation broadens up. And before you take the slides down, because I don't know if the guests have any questions about those, Eric, but I would like to say that we have with us that in addition to David McComas, who will be a speaker later, so welcome again, David, we have the department chair of physics in our university, who is Professor Dr. Abbas Chifchi. And I just wanted to introduce him briefly because he has a PhD from Duke University, and he is our collaborating member of CERN in the Atlas collaboration. So when we're talking about particle physics, he's the man. So that will be in this conversation a very important part of our university. So welcome to the chair of physics. And I see also down at the bottom, upgraded now, as I requested, Ur Murat Lelolu, who is a very good friend and a central figure in the development of the Turkish space program. Maybe Ur could say something about himself, but I've had the pleasure to speak to work with Ur for a long time. Ur, if you would like to say hi to everybody and anything about yourself, this would be a good time. We have a minute.
Okay, thank you, Fabrizio. Hi, everybody. Well, I'm sorry, I'm infected right now, not with COVID, but I can not talk. Anyway, I worked for TÜBİTAK for 20 years. So it is some sort of National Science Foundation plus government laboratories in Turkey. So I was with one of these laboratories, and we practically started the Turkish space program there. We had some technology transfer program from SSTL of the UK. Then we continued with our own satellites, and it is still going on. Then I lived TÜBİTAK Uzay after 20 years. Now, then I joined Middle East Technical University, and mostly I worked in remote sensing. And it's been 10 days that I'm now with another university, the Space Engineering department. Now I will be more involved in space projects in Turkey. Well, that's all. Thank you.
Thank you, Uğur Hoca. I really appreciate your coming. This is great, and I geçmiş olsun. And I didn't ask. I know that the chair of physics is buried with having to process registrations today. But if Professor Abbas would like to say something, please do so. Probably hidden in paperwork right now, so we're gonna let that go. What I would suggest we should do is this. First of all, I would like to thank again our speaker for discussing a subject that is obviously extremely important for rigid body dynamics, that is part of 42, which makes it a very attractive solution to explore these issues. And definitely it's gonna go into the pile of competence that we need to develop. So I really appreciate your bringing that up. And especially I would like to say that I appreciated what one could call the hello world example, that is not only in a way simple, but it is also rooted in an actual space mission that experienced that problem of the interaction between the degrees of freedom in the presence of dissipation. So this is a wonderful presentation. I really appreciate it, Eric. So what I would suggest we do then is that we take a few minutes of break, reconvene at 1500. And at that point, if I understand correctly, Eric will dive into 42 on a deeper. And Eric, you need to reveal the secret of the name, because everybody wants to know. So please get ready for that, okay?
Right.
Thank you.
I'll lead off with that.
All right, thank you so much. I'll see you in what looks like it's 8 minutes then. Thank you.
All right, see you then.
Bye-bye.